Hello all. This class is meant for the students of Computer Science and Allied branches of KTU as per 2024 scheme. In the third module of the paper, we have already discussed the concepts of vector length and unit vector, dot product and angle between two vectors, the Cauchy-Schwarz inequality. Then we introduced inner product spaces. We have given some examples of inner product spaces which are Rn and M22, which are set of all 2 by 2 matrices with real entries. Then we discussed some properties of inner products. Then we generalized the concepts of length, distance and angle to inner product spaces. In today's class, we will discuss orthogonal projections in inner product spaces. What do you mean by orthogonal projection of a vector onto another vector? Here you can see two vectors in the figure, vector u and vector v. And you may note that the angle between two vectors is less than 90 degree. Then to produce the orthogonal projection of u on v, which is denoted by projection of u on v, you have to draw the perpendicular from the tip of u onto v. So this angle is 90 degree here. Then what is the vector produced here? The red line in the figure. It is the vector projection of u on v. So here also you can see that what is meant by projection of v on u. So from the tip of v, you have to draw the perpendicular onto the vector u. Then the new vector produced is called the projection of v on u. And what happens if theta is greater than 90? That is, if the angle between two vectors is greater than 90, then how can you draw the perpendicular from the tip of u onto v? You have to extend v to the opposite direction of v. Then you can draw the perpendicular from the tip of u onto the negative of vector v. So here projection of u on v is a vector which is in the opposite direction of v. Here if theta is less than 90 degree, the projection of u on v will be in the direction of v. And if the angle between u and v is greater than 90, then the projection of u on v in the negative direction of v. So how can you express the vector projection of u on v using the vectors u and v? Here you can see that the angle between these two vectors u and v is less than 90. You may consider this triangle here. So what is cos theta? Cos theta equal to adjacent side by hypotenuse, that is adjacent side the length of the vector projection of u on v. So let me write norm of length of the vector projection of u on v means that it is norm of projection of u on v divided by norm of the hypotenuse, that is the vector u. Okay. So projection of u on v, norm of, that is length of projection of u on v is given by norm u into cos theta. Now, if the angle between u and v is less than 90 degree, you know projection of u on v is a vector in the direction of v. So this vector is actually a constant times the vector v. Projection of u on v can be expressed as a scalar multiple of v. This is the direction of v. So a must be positive. Okay, so this is equal to norm u into cos theta. And since norm of AV is equal to modulus of A times norm V, this can be written as this is equal to norm U into cos theta. And you know A is positive because projection of U on V here is in the direction of V. Therefore, A must be positive. So modulus of A is A itself. So A is equal to norm U cos theta divided by norm V. And here you may multiply norm v on the numerator and denominator. So expression becomes A is equal to norm u into norm v cos theta divided by norm v square. And you have already introduced about the concept of dot products, and you know norm u into norm v cos theta can be written as u dot v. And also norm v square can be written as v dot v. So what we already got is here projection of u on v equal to A times the vector v, and A is given by u dot v by v dot v. Hence, the projection of u onto the vector v is denoted by projection of u on v, and it is given by A times the vector v. That's equal to u dot v by v dot v times the vector v. And in Rn, we typically use the Euclidean inner product unless otherwise stated. So in the problem, sometimes the inner product may not given explicitly, then you can just take the Euclidean inner product, which is a standard inner product on Rn. Now let us have some problems. Find the orthogonal projection of u equal to 2, 1 onto the vector v equal to 3, 4 in R2. So the formula is u dot v by v dot v times vector v. So in R2 we are considering the Euclidean inner product. So you have U dot V is given by 21.34, that is 2 into 3 plus 1 into 4, that is equal to 10. And V dot V is given by 34.34 itself, that is equal to 9 plus 16, that is equal to 25. So you have 10 by 25 times the vector 34, that is 6 by 5, 8 by 5. In the figure you can see that of U, the vector is 2, 1 here, projection of U. V is the vector here, 3, 4. Okay. So projection of 2, 1 onto the vector 3, 4 is 6 by 8, 8 by 5. This vector. This is a projection of U on V. Next problem, find the orthogonal projection of U equal to 6, 2, 4 onto the vector V equal to 1, 2, 0 in R3. So let us use the formula again. Projection of U on V equal to U dot V by V dot V times vector V. So U dot V is given by 6 plus 2 into 2 is 4 plus 0, that's equal to 10. And V dot V is 1 into 1, that is 1, plus 2 into 2, that is 4, that's equal to 5. So you have 10 by 5 times the vector 1, 2, 0. And you can see the figure again. Here you have the three-dimensional space, x, y, z axes are here. And the vectors are U and V. U is 6, 2, 4. U is the vector here, 6, 2, 4. And V is the vector 1, 2, 0. You can see that the set coordinate is 0 here. So the vector is in the xy plane. So this is a vector 1, 2, 0. Okay. And you have to find the orthogonal projection of this vector U onto the vector V. So you can see that this angle is actually 90 degree. This is a projection of the vector onto the xy plane. So it's a perpendicular drawn to the xy plane, and this is 90 degree, and this is a vector 2, 4, 0 is the vector projection of U on V. Now how can we define the orthogonal projection on general inner product spaces? Okay, so let U and V be vectors in an inner product space V, that is a specific inner product is defined on the space V such that the vector V is not equal to 0. Then the orthogonal projection of U onto V is denoted by projection of U on V again, and it is defined by inner product UV divided by inner product VV times the vector V. Let us have a problem. Find the orthogonal projection of U equal to 2, 1 onto V equal to 3, 4 with the inner product given by UV equal to U1 V1 plus 0.25 U2 V2 in R2. So the only difference is that here a specific inner product is given in the problem. So you have to find the orthogonal projection with respect to this inner product. So if such an inner product is not given, you just take the Euclidean inner product. So here the formula is inner product UV divided by inner product VV times the vector V. And when you calculate this inner product UV, you have to use this formula. Okay. So let us find inner product UV. It is equal to inner product, the vector 2, 1, comma, the vector 3, 4, and the formula to be used is U1 V1, that is 2 into 3 plus 0.25 times U2 V2, that is 1 into 4. So actually this will give 7. And inner product VV, likewise you can find inner product VV also, that is inner product 3, 4, comma 3, 4. So use the same formula given U1 V1, that is 3 into 3 plus 0.25 times 4 into 4. So this will give the answer 13. So the answer is projection of U on V is given by 7 by 13 times the vector 3, 4, and it is 21 by 30, 28 by 13. Now you may note down the questions 3, 4 and 5. In the third one, the two vectors is given in R3. You have to find projection of U on V and projection of V on U. You have to write the formulae as accordingly. And the inner product given is this Euclidean inner product. And in the fourth problem, here again projection of U on V and projection of V on U are asked, and the specific inner product is not given. Then also you may consider this Euclidean inner product itself. And in the fifth problem, a specific inner product is given. So you have to find this inner product UV using this formula. That's the only difference. So do the problems by your own, and the answers will be given in the next class.